Hi, George Diamond here. We're getting ready to take a look at a little video here involving the chain rules. We're going to kind of be introducing the chain rule. First, now my calculus students recognize that today I'm carrying with me a yellow measuring tape. So let me set this down. Let's get to our video. Now, basically with this first video, we're just introducing and talking about the chain rule. So we're going to kind of introduce it. We're not going to be looking at a bunch of examples with the chain rule in this video. And that's going to be for the next video. This is video number 1. Video number 2, a bunch of examples. So if you want to see the examples, take a look at the second video. But today we're just introducing the chain rule. Now this is the last of the 4 big rules for derivatives. So the first big rule was the power rule. The second rule was the quotient rule, the product rule, and then last, this is the chain rule. All right, so the 4 big rules for taking derivatives in calculus. Now, this is video number 1, so let's get started. Now, first, this is actually the beginning of chapter 2, or actually section 2.4 in our textbook. So it's actually a second unit. I'm doing it as unit, unit number 4. Now, a couple of essential questions with this unit. We're going to look at first how the chain rule is used to find the derivative of a composite function. Now, after we get finished with the chain rule, we're going to move right into implicit differentiation. Okay, how do we use implicit differentiation to find the derivative of a function? Next, then last, we're going to finish up our unit with related rates. So something called related rates, mathematical modeling. So this will be our next unit. I don't do a unit over the entire chapter, so we kind of cut it back some. This will be our one little unit here for my calculus students. So moving right along, let's get right into the chain rule. Now I want to start off, we use the chain rule to take the derivative of composite functions. Some functions, a lot of functions we don't need to use the chain rule on, some that we do. So we're going to take a look at some functions we can do without the chain rule. So in this column here, all of these functions we don't need the chain rule with. And then over here, we're going to look at functions we have to use the chain rule with, or probably the easiest way would be to use the chain rule. So these, we don't need the chain rule. These over here, we're going to need the chain rule. So let's get started. First, y equals x squared plus 1, we don't need a chain rule for this. It's the power rule. The derivative of x squared is 2x. That's your derivative. No chain rule. Now, the next function over here, let's come over here. We have y equals the square root of x squared plus 1. Now, this is a composite function. So the square root of x squared plus 1, that's a composite function. That's part radical and part polynomial. So this is a composite function. If we're going to take the derivative of this function, we would need the chain rule for that. Now, next, we don't need the chain rule to find the derivative of y equals sine x. The derivative of sine x is cosine x. We looked at that in a previous video. So we don't need a chain rule for this particular function. However, y equals sine 6x, this you would need a chain rule. Okay, this is part trig function, part linear function. So we're going to need a chain rule for this right here. Okay, let's look at one that we would not need a chain rule with. Y equals 3x plus 2. The derivative of y equals 3x plus 2 is 3. Okay? Now, taking this same function, let's take a look at a problem that we would need to use a chain rule. Y equals the quantity 3x plus 2 to the 5th power. Now that we would need to use the chain rule. You got a power of 5, unless you want to try to expand it and simplify it as a big polynomial, but this problem here would be much easier to use the chain rule to find the derivative of. Another example, y equals x plus tangent x. Okay, we don't need a chain rule for this. However, y equals x plus tangent squared x, this we have to use the chain rule. So we just want to start off looking at a few problems here, just a couple of functions really, where we would have some we would not need a chain rule with. These over here we would have to use the chain rule with. These over here are composite functions, and composite functions you have to use the chain rule. So let's get started here. Let's take a look at a little problem I've got set up here. Let's take a look at y equals 9x squared plus 6x plus 1. Now we're going to find the derivative of this little polynomial. Now, first of all, let me mention, we don't need the chain rule to get this derivative. Okay, that's just the power rule. If we're going to get the derivative of 9x squared is 18x. The derivative of 6x is 6, and the derivative of 1 is 0. So we don't need the chain rule to get the derivative of this, but I'm going to use it to illustrate the chain rule. So what we're going to do, here's our original function. It's a little trinomial, little quadratic. I got it written again over here. Now, first of all, this is a perfect square trinomial. So I want to rewrite this trinomial in as a binomial square. So we'll put it in factored form like so. All right, so these are the same. This is just in factored form. Y equals the quantity x plus 1 squared. So we write it as a binomial square. So it's a perfect square trinomial. So we're going to write it in factored form like so. Right. Now, when you write it in factored form, you can kind of notice two parts of this function. First of all, it's raised. You have a quantity inside your parentheses. 3x plus 1 is a linear, function raised to the second power. This kind of has two parts. When you look at this problem now, you've got your exponent, and then you got what's inside the parentheses. So typically with the chain rule, you're going to have an outside part of the function and an inside part of the function. The outside part is the exponent. The inside part is the 3x plus 1, what's inside the parentheses. So what we're going to do is we're going to kind of take this apart, and we're going to describe the inside part and the outside part as two separate functions. So we're going to start off, let's let u equal 3x plus 1. All right, so let's let u equal 3x plus 1, and I'm going to write u equals 3x plus 1 over here. Now that's our inside function, u equals 3x plus 1. Now let's describe the outside part of the function. Now the outside part of the function is the exponent. So we're going to let y equals u squared. So if u equals 3x plus 1, so the outside part of the function becomes y equals u squared. And we're going to put this right here. Now first, let's go ahead and describe the derivative of the original function. The derivative of 9x squared is 18x. The derivative of 6x is 6. So here's the derivative of the original function. Now, when you take that derivative, notice now you're taking the original function is in terms of y and x. So when you take the derivative, you're taking the derivative of y with respect to x, right, which is 18x plus 6. Now, let's take the derivative of the inside part and the outside part. Right, the inside function and the outside function, if you will. Okay, let's start off with, I believe we start off with y equals u squared. This is the outside function, if you will. Now, this function is described in terms of y and u. So when you take the derivative, we're going to take the derivative of y with respect to u, okay, which is dy over du. Now, not dy over dx, okay, dy over du, which is 2 times u. Now remember, we said that u is equal to 3x plus 1, so I'm going to do a little substitution here. Let's take the 3x plus 1, and I'm going to substitute it back over here for u. And this derivative becomes dy over du is 2 times the quantity 3x plus 1 now. So we're going to take since u is 3x plus 1, we're going to substitute it in. Right, so that's the derivative of the outside part of the function. Now, let's take the derivative of the inside function. U equals 3x plus 1. Now, this time, we get the two variables we're working with here is u and x. So this time, we're going to take the derivative of u with respect to x. So this will be, we're going to describe this, well, we go ahead and multiply this by 2 first. 2 times 3x is 6x. 2 times 1 gives us 2, so it'll be 6x plus 2. Okay, now let's take the derivative over here, or the inside part of the function. Now, the derivative of 3x is 3. The derivative of 1 is 0. So this would be du over dx equals 3. Right, so this is the derivative of the outside function, that's the derivative of the inside function. Now notice, the original function was 18x plus 6. Now, notice what happens. The derivative of the outside function, 18x plus 6, is going to equal the derivative of the outside part of the function times the derivative of the inside part. So if you take 6x plus 2 times 3, you get 18x plus 6. That's the chain rule. Right, so we're going to write it like so. So you can see this is the original function. Okay, this is the derivative of the outside part. 3 is the derivative of the inside part. So when you look at the chain rule, if you look at it in your textbook, this is what it will see. Say dy, the derivative of y with respect to x is equal to the derivative of y with respect to u, okay, times the derivative of u with respect to x. So this is our chain rule. So let's go ahead and move on. We look at a couple of short examples here on the PowerPoint. I'm just going to kind of point to them to kind of show you how this will be set up. And like I said, we're going to look at a lot more, several more involved examples in a little while in the next video. So dy over dx equals dy over du times du over dx. Now this pattern is called the chain rule. Now the reason we call it the chain rule is There are instances where you may have to use the chain rule more than one time to find the derivative of a particular problem. Now, we'll look at one of those, look at an example or two like that on our next video. Now, the chain rule, this is it. dy over dx equals dy over du times du over dx. All right, so this is the derivative of the outside function times the derivative of the inside function. So typically written like this. Okay, this is the way I write it. So the derivative of f of g of x. Now, f of g of x is how you indicate a composite function. Okay, f is the outside part of the function. G of x is the inside part of the function. So as you take the derivative, you take the derivative of f, that's f prime, leave the inside the way it is, times the derivative of the inside. So when you take when you use the chain rule, you take the derivative of the outside, so outside prime, times the derivative of the inside. Now when you take the derivative of the outside, you bring the inside function down with it. So you don't do anything to the inside function, then times the derivative of the inside function. So the chain rule, so we'll think of an outside part. So a little note here, I wrote this. It's helpful to think of the composite function, f of g of x, as having two parts, an inner part and an outer part. Right, so as you take the derivative now, we take the derivative of the outside, leave the inside the way it is, times the derivative of the inside. Now, let's do a little example here. Let's try a little trig problem. Y equals sine x squared minus 4. Now, as you look at this function, okay, first of all, the outside part of the function is the sine part, the trig part. And what's inside the parentheses, that's the inside part of the function, the x squared minus 4. So this composite function is, the outside part is the trig function, the inside part is the parabola, is the quadratic x squared minus 4. All right, so this is the outside, that's the inside. So when we take the derivative now, using the chain rule, we're going to take the derivative of the outside. Now the derivative of sine is cosine. And you leave the inside the way it is, you bring the inside down times the derivative of the inside. So it go like this. So once again, this is like so. So the derivative f of g of x is the derivative of the outside, leave the inside the way it is, times the derivative of the inside. So looking at this derivative here, remember the derivative of sine is cosine, so the cosine x squared minus 4. So you take the derivative of the outside part, bring the inside down, times the derivative of the inside. So this is the way our derivative will go. So the derivative of sine is cosine, bring the x squared minus 4 down, right? And then times the derivative of the inside, which is the derivative of x squared minus 4. Now, let's go and get our derivative. Now the derivative of x squared minus 4, the derivative of 4 is 0. The derivative of x squared is 2x. As you describe your derivative, this is it. It's cosine x squared minus 4 times 2x. Now you can put the 2x first if you want to, but this is it. So remember now, the derivative of the outside, cosine, leave the inside the way it is, times the derivative of the inside. That's the chain rule. In this case, you end up with cosine x squared minus 4 times 2x, okay, which is 2x cosine x squared minus 4. Now we do some more of these examples, like I said, on the next video. Let's look at another one here though on our PowerPoint. Okay, so you can find the derivative of y equals cosine 3x. Now to get started, first of all, you want to notice that cosine is the outside function, 3x is the inside part. So what's inside your parentheses typically, that's going to be the inside part of the function. So, now, we know the derivative of cosine is negative sine, right? So we're going to take the derivative of the outside, bring the 3x down, times the derivative of 3x. So if you do this, this is the way it will look. The derivative of sine is, derivative of cosine rather, is negative sine, bring the 3x down, times the derivative of 3x. So the derivative of the outside part, bring the inside down, times the derivative of the inside. Now hopefully after you do a bunch of examples and we look at this for a while, you'll be able to do the chain rule very quickly, right? Now the derivative of 3x is 3, right? So if you bring the derivative down, you'll get your derivative to be negative sine x, 3x times 3. Or if you prefer, negative 3 times sine x, 3x. That's the derivative. Okay, using the chain rule. So the derivative of the outside, negative sine, bring the inside down, times the derivative of the inside. Okay, let's try, see if we have another one. Yeah, let's try another example here. We'll do this one here. We'll do y equals secant x squared. So y equals secant x squared. Now, before we look at our example here, though, remember the derivative. So the derivative of secant squared is secant tangent. So you remember this? So as you take the derivative, the Secant will be the outside part of the function. X squared is the inside. So what we're going to do is we're going to take the derivative of the outside. The derivative of secant is secant tangent. And then we'll take the derivative of the inside, the derivative of x squared. So if you take our derivative now, that's your outside part. This is the inside part. So we take the derivative, now the derivative of secant x would be secant x tangent x. So the derivative of secant x squared would have to be, here it goes, okay, secant x squared tangent x squared. Remember, take the derivative of the outside, you bring the x squared down, bring the x squared down, times the derivative of x squared. So take the derivative of the outside, here the secant is secant tangent, bring the x squared down, times the derivative of x squared. Now the derivative of x squared is 2x, so we're going to write our derivative like so. That's the derivative. Now you can't bring the 2x out front, it doesn't really matter, I guess. So it'll be 2x times secant x squared times tangent x squared. That's the derivative. So remember now, secant is the outside part, the derivative of secant is secant tangent. So it'll be secant x squared tangent x squared times x squared. The derivative of x squared, which is 2x. So this is our derivative here. Okay, let's move on. Now this brings us to what's called the general power rule. Okay, so we looked at the power rule earlier. That's our first major rule for derivatives. Okay, well this is described as the chain rule, really. Right? So we take the derivative of u to the n. Right? So u to the n power. You got an exponential term or function of some type. As you take the derivative now, you're going to bring. Remember, you're going to bring the n down front. The n becomes a factor. So it'll be n times u to the n minus 1 power. But now times the derivative of the inside part. So take the derivative of the outside, bring the u down, times the derivative of u. So the derivative of the outside, leave the inside the way it is, times the derivative of the inside. So just a little introduction here to the chain rule. All right, and like I said, in our next video number 2, we'll look at a bunch of examples, and then we'll kind of see if we can work those through. But this is called the general power rule. In calculus, we use the general power rule all the time. So the chain rule, we use it quite a bit. It's a major rule. We got to get good at this. So that's why we're going to look at a bunch of examples. So once again, this is the outside part of the function. So the derivative of the outside, leave the inside the way it is, times the derivative of the inside. So that's the chain rule. Derivative of the outside, bring the inside down, times the derivative of the inside. Okay? And let's take a look at, now I'll be looking forward to you seeing the next video.